Okay, let's take a look at lesson 74. We're moving right along. We're going to be talking about uniform motion problems today when we have both distances that are given. Some of the ones that we've been looking at so far are, and I'm going to kind of illustrate them slightly different than we're used to seeing, but see if you can follow me. So we have seen problems where we'll have two different people or two different trains or two different cars or two different runners or whatever. And this represents distance, okay? So from here to here is the distance that perhaps someone is running or whatever. So we have the distance of the first person or whatever and the distance of the second. So we've seen problems like that where we've had, remember, distance is rate times time, right? So that means rate times time would be the distance here like this for the first one. And then rate times time on the second guy would be the distance. Okay, so we've seen problems like that where they're running in opposite directions, but they're running the same distance. We've also seen problems where the distance might look like this. And perhaps we're told that the distance is 120 miles. And we've got a person that's running in this direction. And we have a person perhaps that's running in this direction. Okay, and we know that the total is 120 miles. So you could add together, the rate, the distance of each runner. And to get the distance, we do rate times time, right? And I know you guys aren't used to seeing it this way, but we want to do it this way today because we've been working so much with subscripted variables that this is a great place to apply that knowledge, okay? And the third thing that we've already seen with problems, just to kind of show you an illustration, would be that you might have a person who's running, let's just say, two people who are running a certain distance. And we know that there's 40 miles left from here where I'm going to put a little dotted line, okay? So maybe the first person has only run this far and it would take 40 miles to get to the final distance where this one has already run, okay? So we would take, to find the distance of the first guy up there, you take the rate times the time. That gives you his distance. But we'd have to add 40 to that in order to equal the distance of this guy on the bottom. So then you would, for distance, it's always rate times time, right? Okay, so those are the things that we've been working with. Now, we've been using the table, understandably, but today we're not going to use the table because it would make it very complicated to try to do that. So we're going to start off with an example, and if you have your books, you're certainly welcome to turn to page 309. 74.1 is the problem that we're going to look at. Okay, so the first thing I'm going to do is I'm going to read this word problem out loud, and then we're going to set up 4 different equations that represent distance and time and the rate of what's happening in this word problem. So let's go ahead and read it. Friar Tuck rode the 24 miles to the fair in Nottingham at a leisurely pace. He stayed too long at the fair and had to double his speed on the way back in order to get home in time. If his total traveling time was 9 hours, how fast did he travel in each direction and what were the times? So we're going to set up 4 equations for this word problem. We're going to call them A, B, C, and D. Okay, that's the first thing we want to do. So let's think about this. We're told that he rode 24 miles to the fair. Okay, so we're going to call that going. So we're going to set up, he's going to the fair. So so we're trying to figure out the distance here. The distance is 24 miles, right? So what is distance? Distance is, let's write that up here. Distance is always rate times time. Okay, so we're going to put the rate of him going to the fair times the time of him going to the fair, that's what the G stands for, is equal to 24 miles. Okay, that's what the first part of the problem says. Now, the rate or the distance coming back home is also 24 miles. So we're going to call that the rate back times the rate coming back times the time coming back. That's a lot of times words in there, is also 24 miles, right? It was 24 miles going to the fair and 24 miles coming back from the fair. Okay, so that's where we're getting those little subscripts G and B, just so you know. So it's rate times time going to the fair equals 24 miles, and rate times time coming back from the fair was 24 miles. That equals the distance. Okay, so there's two equations. Now the third one, let's see here what else we have to know. He stayed too long at the fair and he had to double his speed on the way back. All right, so the rate coming back, how do we look at that? Was 2 times the rate going, right? He went twice as fast as the rate that he went to the fair, going to the fair. So we're going to have 2 times the rate going to the fair, right? That's what that means. He went, let's write that over here. He doubled. What that is saying is he doubled, or 2 times, right? The amount. He doubled his rate or his speed, which is the same as speed. Rate is always the speed, like miles per hour. So he doubled his rate on his way back from the fair. So that's what that says. That says his rate coming back was doubled the amount that he was traveling going to the fair. Okay, I know it almost sort of kind of can sound complicated because the subscripted variables are tough to keep up on, but you're going to get the hang of it, I promise you. And then a fourth one here, we have to address the time. It says his total traveling time was 9 hours. So let's think about that. Total time. That means the time that he spent going to the fair and the time he spent going back from the fair totaled 9 hours. So total means let's add that. Oh, so let's write the last one here. His time going plus his time coming back was equal to 9 hours. Now, we know from working with these, we're going to kind of twist this thing around a little bit. I'm going to set this as the time back equals 9 minus the time going. Okay, we just want to re-express that because I need to use one of these variables. All right, so now we have some good stuff to work with. So we need to find our base equation. And our third one usually is what helps us determine which one of these is going to be our base. Well, it looks like B is a good base. So we're going to use that for our base because I can take and substitute in C in for R sub B. So let's rewrite RB, TB. That's the rate times the time of him coming back from the fair equals 24. And I'm going to take C here. I'm going to take C and I'm going to substitute it in for RB. So for RB, we're going to put 2RG. And for TB, look here. This is going to be very nice. So for TB, we're going to substitute in 9 minus T sub G equals 24. Now let's do the distributing here. We have 18R, whoops, that should be a tinier G. That should be a subscript. I got carried away. There we go. Okay, so I have 18R sub G. And then I'm going to take this and multiply. We're going to have minus 2R sub G, T sub G equals 24. Is there anything else I can substitute in? Ah, yes, there is. Look right here. We have a value for RGTG. So right down here, we're going to put in that value, 24. So let's rewrite 18R sub G minus 2 times 24 equals 24. Now let's just do the math here. Notice what happened. This is why this turns out to be a beautiful thing, because now I'm finally left with just one variable. I can solve for the rate. So in other words, how fast did he travel going to the fair? That's what we're going to solve for here. So let's just work this out. Now let's hope that 72 is divisible by 18. Let's plunk that in the calculator and see what we get. All right, you're going to get 4 miles per hour. So the rate that he traveled going to the fair was 4 miles per hour. Now from that, let's look at the next part of this. So this was the first thing we did. So I'm going to put a big Roman numeral 1 right there. Now below that, I'm going to do a Roman numeral 2. And we're going to look at the next part of this. Let's figure out the rate that he traveled back from the fair. Okay, so let's go find the rate coming back from the fair is actually equation C up there up top. RB equals 2RG. So let's write that down here. This is going to be the second part of it. And we can plug in, we just solved this right here. So we can take RG, the value for RG, and plug it in. And then we can find the rate that he traveled going back from the fair. So going to the fair was 4 miles per hour. So there's the rate he traveled coming back from the fair. Okay, so there's 2 parts of it. And they asked us to solve for that. They wanted to know how fast he traveled, or his rate. How did they actually word that? How fast it, oh wait, I'm looking at the wrong one. Okay, how fast did he travel in each direction? So going to the fair, he traveled 4 miles per hour. Coming back from the fair, he traveled 8 miles per hour, which makes sense because remember, it said he doubled his speed on the way back. So he went 4 going, he doubled it and traveled 8 miles per hour coming back. So that's perfect. That makes great sense. Now let's look at Roman numeral 3. We need to figure out the time that it took him to travel to the fair, going to the fair, and then how long did it take him to travel back home when he left the fair. So let's solve for the time it took going to the fair. Do we have something here? For TG. That's what we want to solve for. Well, let's go up and look at our equations. We can use RG/TG. Let's write that one. That's equation A. RG/TG is equal to 24. Because now I can substitute in RG was 4. TG is what we're going to solve for here. The time going equals 24. So we're going to divide by 4. The time it took him to go to the fair was 6 hours. And then finally, for number 4, we want to find the time it took coming back from the fair. So let's go find an equation here. Oh golly, we can use different ones. We can actually use D, we could use B. I think I'm just going to go ahead to choose to use, oh golly, we can use D. So we'll use D, and D is TG plus TB equals 9. So we're going to plug in our TG that we just solved with 6 plus TB equals 9. We'll subtract 6 from both sides. The time it took to get back from the fair was 3 hours. So we just solved 4 pieces of information using the distance formulas that we could set up using rate times time, and then also just trying to break apart the word problem and get it into other equations. And we made our 4 equations up here that I'm highlighting. And once we figured out those 4 equations, then we were able to do what we've been doing in the last several lessons, where we substitute in. So you see why the table is not going to be helpful in these problems. It's going to be better for us to just use those subscripted, those subscripted variables. Okay, so that was 74.1 in your book, I believe. Yeah, so now we're going to build one into your notes. So let's go ahead and get your packets ready. And right up here, I'll look at this word problem right here. All right, here's an interesting name, Atalanta. Guess that's the name of a runner. Atalanta ran 4 times as fast. I'm going to highlight some important information here. So Atalanta ran 4 times as fast as her challenger. In fact, she ran 80 miles in 2 hours less than it took her challenger. How fast? Oh, I'm sorry, I didn't finish that. 2 hours less than it took her challenger to run 28 miles. How fast did each of them run, and how long did they run? All right, so we have to set up some equations here, which I've actually already done for you. So let's look at these. Kind of get a picture of what's happening here. So we have the distance. Think about this. I'm going to write this in here because I want you to see this. So we have the distance of Atalanta is 80 miles, right? She ran 80 miles. The distance of her challenger, which we're going to call D sub C, was, let's see, the challenger ran 28 miles. Oops, I should go back there and highlight that. The challenger ran 28 miles. Okay, so they ran different distances. Okay, so let's look at the expressions that and the equations that we set up to represent all of these items in the problem. All right, so what is the distance of Atalanta? Well, distance is always rate times time. I'm right down here looking at letter A. So the distance of Atalanta is going to be rate times time. So we're going to write that as the rate of Atalanta times the time of Atalanta equals the distance of Atalanta, which we know is 80. So we can actually replace this with 80 right here. Okay, look at B. The distance of her challenger is still going to be rate times time, but it's going to be her rate times her time. So the distance of the challenger is the rate times time. So that's going to be the rate of the challenger times the time of the challenger equals the distance of the challenger. And the distance of the challenger we said is 28. So we can just replace that with 28 right there. Okay, so far so good. The rate of Atalanta. All right, we're given some information about the rate of Atalanta. Let's go back up here. Atalanta ran 4 times as fast as her challenger. So here's how we write that expression. The rate of Atalanta, look, I'm right over here. The rate of Atalanta is equal to 4 times the rate of her challenger. That's what it said in the problem. She ran 4 times as fast as her challenger. So what is Atalanta's rate? 4 times the rate of the challenger. And so that's how we get equation C. Now let's look at the last one here. We have to figure out the time of Atalanta because we're trying to figure out how fast they each ran and how long they each ran. So the time of Atalanta is, according to the problem, she ran 2 hours less than it took her challenger to run her distance. So 2 hours less than the time of the challenger. So the time of Atalanta, look at equation D. The time of Atalanta was 2 hours less than her challenger's time. So that's how we get the challenger's time right here minus 2. That is how we figure out the time of Atalanta. Okay, I wish they didn't use these weird, strange names. They use those weird names that makes half of it seem so much more than it really is. But anyway, so there's our 4 equations, A, B, C, and D. So now let's figure out how we want to work this out. Well, first of all, let's make sure that we are all set and ready to roll. And yes, we are. Okay, so Roman numeral 1. We're going to figure out which one of these is going to be our base equation. Should we choose, look up here at A and B, should we choose this one or should we choose this one? Well, let's look at the third equation C. I have RA equals 4 times RC. So I'm going to go back up and use equation A because I can plug in this value, can be plugged in right here. Okay? Okay. So let's use RA, TA And you really say that R sub A times T sub A, but I'm just going to, it's just too much to say. So I'm just going to say RATA equals 80. And we're going to plug in for RA, it's 4RC. 4RC times TA. Oh, but wait a minute. We have a value for TA, don't we? So let's plug that in. Let's not rewrite it. Let's look at equation D. Equation D says TA equals TC minus 2. So let's put that in right here for TA. TC minus 2 equals 80. Now let's do our multiplication here. I'm going to have 4RC TC minus 8RC equals 80. Is there anything else I can substitute while I'm at it? Look here, RCTC. Go look at equation B off to the right. RCTC is equal to 28. So let's put 28 in there. Minus 8RC. And the beautiful thing here is that we have managed now to simplify it down to just one variable. So now we can solve for the rate of the challenger. So 4 times 28 is 112. Minus 8RC equals 80. Subtract 112 from both sides. Negative 8RC equals negative 32. We'll divide by negative 8. That'll get rid of our negatives. And we'll have the rate of the challenger is 4 miles per hour. And you might want to write here, that's the rate of the challenger. And that is what R sub C stands for. The R is the rate and the C is the challenger. Okay, so we just figured out the first part of the question. The first part of the question is how fast did they each run, okay? So we figured out that the challenger ran 4 miles per hour. Now let's move on to number 2, Roman numeral 2. Roman numeral 2, let's figure out the rate of Atalanta. All right, so we're going to go find an equation up here that might already help us start that. We'll look at equation C. Equation C says the rate of Atalanta is equal 4 times the rate of the challenger, which is perfect because in Roman numeral 1, we solved for the rate of the challenger. So we can just go plug that 4 in for the rate of the challenger. And we'll be able to figure out very quickly the rate of Atalanta. The rate of Atalanta is 16 miles per hour. Okay, and does that make sense? Because in the problem, go look at example 1 up here. I'm going to circle with purple so you can see where I'm at. Atalanta ran 4 times as fast as her challenger. So does that ring true now? Says she ran 16 miles per hour. Is that 4 times as fast as the rate of the challenger? Yes, it is, because the challenger ran 4 miles an hour. So 4 times 4 is 16. So right under here, this is the rate of Atalanta. Just so you remember, so that's R sub A. All right, let's look at Roman numeral number 3. Roman numeral number 3, now we have to find how long they ran. So now we're looking for time. Okay, so what do I know here? I have the rate of Atalanta. So let's go look at the first equation up here. Letter A, the equation in A is RATA equals 80. We want to use this one because I now have the rate of Atalanta. So when I plug that in, then I'm going to be left with the time of Atalanta. So I'll have that part of the problem figured out. So let's substitute in 16 and solve for T sub A, which is the time of Atalanta, and 80 divided by 16 is 5 hours. So now we have figured out the third part of the problem, which was the time. Underneath here, let's write the time of Atalanta, T sub A. And the last part is going to be right underneath here, Roman numeral 4. We need to figure out the time of me just a second. I think what do I have? RCRATA. Okay, so I need the time of the challenger. Okay. All right, so let's go back up here and see where can I use the time of the challenger. Well, there's a couple different places we can go, but I'm going to use letter D because I haven't used that one to solve for something. So we'll go ahead and use TA equals TC minus 2. Actually, that's not true. I did use it over in Roman numeral 1, but we're going to use this because I can fill in 5 for the time of Atalanta equals TC minus 2. And this will be really quick and easy to get. So the time of the challenger is 7 hours. And that is, we'll write right here, time of challenger. If you can fit it in there, I'm going to run off my page. That's the T sub C. Okay, so we managed to figure out both the rates and the times for each one of those runners. Okay, so that's how we work those out. The challenge sometimes is just remembering that distance is always rate times time. The subscripted variables just help you identify which runner you're talking about or which train you're talking about or whatever the problem is about. Okay, so separate those out. Remember, rate times time is distance. And then sometimes you have to take your time and then try to set up your equations as the word problem lays it out. That's the challenging part, but I know you can do it. Okay, so let's do our practice problem. And if you would like to pause the video and see if you can figure this out on your own and then come back and check your answers with me, that is 100% okay with me to do that. I'm going to go ahead and work through it. If you want to stick with me while we at least set up the equations, that's fine too. However you want to do it is fine. So it's on page 310. The practice problem reads like this. Bernard raced twice as fast as the local, what is that word? Domestique. For this reason, he raced 120 miles in 3 hours less than it took the Dominique to race 105 miles. How fast did each of them race, and what was the time of each racer? Okay, so far what I see is we know this is a distance problem because we see rate, we see time. So we're going to set up some things here. We're going to figure out, first of all, oops, got to get my pencil back rolling. I'm going to go to blue now just for something to, actually I'll use green. I haven't used green. We need to figure out the distance of Bernard. Okay, that can be A. We're going to do our 4 different equations. We need the distance of whatever that Dominique is. Domestique. I'm going to have to look that up. I don't even know what that is. Domestique. And actually, I'm going to make it a capital D just because in my subscripted variable, I want it to be a capital D. So domestique. And we need to write something for the rate of Bernard. And we'll write something for the time of Bernard. And I'm choosing Bernard because he's the lead character here. We have more information on him. And so we're going to use him kind of as our lead guy. Okay, so let's write the distance of Bernard. Remember, distance is rate times time. So we know it's going to be the rate of Bernard times the time of Bernard is going to equal the distance. Do we know the distance? Let's go back to the problem. It says Bernard raced twice as fast as the local domestique. For this reason, he raced 120 miles in 3 hours less. Okay, there it is, 120 miles. Okay, there's our first one. The distance of domestique is going to be the rate times the time of domestique. So R sub D times D sub D, T sub D equals, and let's see what is the distance that domestique raced. Well, it says here, for this reason, Bernard raced 120 miles in 3 hours less than it took the domestique to race 105 miles. So there it is. There's the distance of the domestique. What is the rate of Bernard? All right, now we got to figure out what is rate. Rate is speed, miles per hour. Okay, so let's go back into the problem and see if we can come up with an equation for his rate. All right, so Bernard, and I'm going to write this out. Okay, so Bernard raced twice as fast. So I'm going to rewrite that as 2 times faster. I want you to write that down because I want you to see how we come up with this. 2 times faster than the local domestique. So faster than domestique. Now, how do we write that? So the rate of Bernard, it says, is 2 times faster than domestique. 2 times faster than the rate of domestique. Okay, so there's the third equation. And finally, the time of Bernard. Well, we know this is going to be, well, actually, we're going to write this out as well. So let's read this again. Let's find this in the problem. So let's see, ran twice as fast. Okay, for this reason, Bernard, this is the second sentence. For this reason, he, which is Bernard, raced 120 miles in 3 hours less than it took domestique. So 3 hours less. So let's write that down. 3 hours less than domestique. How do I write that? So the time of Bernard is equal to 3 hours less than domestique. So take domestique's time and subtract 3. There's your 4 equations. So let's start. I'm going to put a little line here to kind of separate all this. And we're going to go and start with number 1. All right, let's figure out what is our base equation going to be. Well, let's see. So A is RB, TB equals 120. B shows us the distance of domestique. C gives us a value for RB. So let's use the first equation, A, up here, which is RB, TB equals 120. Okay, and we're going to substitute in, look at equation C. We're going to substitute in, let me underline it here in yellow. We're going to substitute that in for RB. So we're going to put in 2 RD. And then for TB, we also have a value. Look at equation D. Let's substitute that in. TD minus 3 equals 120. Let's do some solving. We're going to go ahead and distribute this. We're going to have 2 times RD TD minus 6 RD equals 120. Is there anything else I can substitute in? I notice this value right here, this variable RDTD. We'll look at B up here. I've underlined it in yellow. Equation B has RD times TD is 105. So let's put that in right down here. And the great thing about that is you know you're on to success because I've narrowed it down to one variable. I'm going to solve for R sub D now. Alrighty, so 2 times 105 is 210 minus 6 RD equals 120. We're going to subtract 210 from each side. Let me work through this. All right, so the rate of domestique is 15 miles per hour. Okay, so we figured that out. Good job. I'm going to put little lines here to separate these. Roman numeral 2. Let's figure out, doesn't matter which one you want to pick. I'm just going to go ahead and say, let's find the time of domestique. I found the rate of domestique. Let's find the time of domestique. We'll just kind of stick to that for right now. So the time of domestique, do we have something up here that represents that? Where do we see TD? Let me erase what I just did because I don't have an equation that starts like that. But I need to pull one that has TD in it. So I'm just going to pull equation B, which is RDTD equals 105. And the reason I want to pull that one, obviously, is because I just solved for R sub D. So I'm going to go ahead and put 15 in for that. And I'll be able to figure out the time. We'll divide by 15 on both sides. and T sub D is 7 hours. Okay, so we have successfully figured out the rate and time of domestique. Let's go ahead and put Roman numeral 3 right up here. And we are going to solve for, let's say, the time of Bernard. And do we have something here? Yes, look at D. Look at equation D up there. T sub B equals T sub D minus 3. I'm going to put T sub D in, which is 7 minus 3. So the time of Bernard is 4 hours. And we can always double check. What did the word problem say about the relationship between the time of domestique and the time of Bernard? Didn't it say, look at equation D that you wrote up there, the time of Bernard is supposed to be 3 hours less than domestique. Is it? Yes, because domestique's time was 7 hours, Bernard's is 4, and that is 3 hours less. So that works out perfect. It matches what the problem says. Now let's look at number 4. Okay, the last thing we have to solve for is the rate of Bernard. So we're going to put the rate of Bernard, and do we have an equation up here? Yes, we do. Look at C. RB equals 2 R sub D. Okay, let's fill this in. I know that R sub D over here in Roman numeral 1 we solved was 15. So to find Bernard's rate, we're going to plug 15 into this, and RB is going to be equal to 30 miles per hour. And let's just verify that our problem said, did he run 2 times faster? Did Bernard run 2 times faster than domestique? Yes, that is look at equation C that we wrote out. The rate of Bernard is 2 times faster than domestique. Is it true? Look at that. He ran 30 miles per hour and domestique ran 15 miles per hour. So yes, that is 2 times faster, isn't it? All right, so that's how you solve those. I think that you'll have fun with those. The most challenging part, as I said, is to set up those equations to start with. But once you get those set up, move forth with the problems. Double check when you're done that everything matches what the problem actually said. Okay? And that is it for your lesson, guys. Have fun with it and have a great weekend, and I'll see you next week.